So today we'll start first this tabular column, which is very important for the competitive side, not for the NCERT point of view side. Can you hear me properly? Hello.
Yes, sir.
Okay. So these are the 6 different types of structures: Roxul structure, zinc blend, quartzite, cesium fluoride, fluoride, and antifluorite structure. So compulsory will get one question on this type of structures. Okay. So if you take the rock salt structure, so rock salt structure is nothing but the NaCl type of structure. So in this type of structure, the Cl minus ions occupy the CCP lattice, and Na plus ions will occupy all the octahedral voids. So if you take the NaCl type of structure, the Na ion will be smaller in size, right, than the Cl minus ion. So Cl minus ion occupies all the CCP type of CCP lattice points, and Na plus ions will occupy the octahedral voids present in that structure. Then the coordination number of Na plus and the Cl minus will be 6 in both the cases. The coordination number for both Na plus and Cl minus will be 6. And the number of unit cells, how many are there? 4. That means it belongs to FCC, right? Yes or no? It belongs to the FCC. So you can say NaCl structure wherever they are given in the question. NaCl structure now, then you have to take it as a FCC type of structure. Okay. And examples for these type of crystal lattice is shown by lithium, sodium, potassium, rubidium, and halides. Rubidium halide, sorry. Or NH4Cl, NH4Br, or NH4I. AgCl, AgBr, MgO, AgF, CaO, TaO, FeO, and the NiO. So compulsory you have to by heart this tabular column, which is very important theory question from this tabular column for the competitive side. If you see the previous questions also, they'll ask like what is the coordination number of Na plus ion in the rock salt structure? What is the answer? What is the answer? What is the coordination number of Na plus ion in the rock salt structure? What is the answer? Answer is 6, right? The coordination number will be 6. Okay. So next one is the zinc blend type of structure. So when you take the zinc blend type structure, that is the ZnS type structure. S minus 2 ions occupy the CCP lattice, and Zn plus 2 ions occupy alternate octahedral voids. So in the case of zinc blend structure, anion will occupy the CCP lattice, and the cations will occupy the alternate octahedral voids. Okay. Sorry, that is wrong. Actually, that is a tetrahedral voids, because Zn plus 2 is forming 4 and Sn minus 12 is forming 4, right? So the tetrahedral voids, actually alternate tetrahedral voids. There is a small mistake in this. So you can correct it in the notebook. The tetrahedral voids, not the octahedral voids. Okay. So the Zn plus 2 structure in this case, S minus anions will occupy the CCP lattice, and the cations will occupy the alternate tetrahedral voids. So that total Zn plus 2 coordination number will be 4, and the S minus 2 coordination number also will be 4. Because if you take CCP lattice, Total number of atoms is 4. Tetrahedral voids will be 4. Octahedral voids will be 8, right? So alternate it is occupying. That means only 4 octahedral voids will be occupied. Remaining 4 will be empty. So that is what explaining in the description part. Zn plus 2 will have the coordination number 4 and S minus 2 also will have the coordination number 4. And number of atoms per unit cell is also 4. Okay. So it is mostly commonly shown in the case of ZNS, ZNO, CDS, BEO. Okay. The next one is a ZNS is shown in the case of ZNS, BES, CuCl, CuBr, CuI, AgI, and the HCS. These are the most common crystal structures which are shown the zinc blende structure. Next one is a woodsite. So it is also one type of ZNS structure only. Okay, but what is the difference here between the woodsite and the ZNS? In the case of woodsite, S minus is occupying the HCP lattice, not the CCP lattice. So anions are occupying the HCP lattice, and Zn plus 2 anions are occupying the alternate tetrahedral voids. In the case of zinc blende, it is a CCP lattice. In the case of woodsite, it is a HCP lattice. So that is only the difference part. And again, the coordination number will be same. Zn plus 2 and the S minus 2 both will have coordination number 4, which is mostly common in the case of ZNS, ZNO, CDS, and the BEO. Okay, next one is the cesium chloride, CaCl. Cl minus ion will occupy the BCC type of structure. BCC means what? Body centered structure. And the Cs plus ions occupy the body of the cube. Okay, that means Cl minus will form the all the corners. Whatever the corners are there in the BCC structure, Cl minus ions will occupy. And the cation Cs plus ion is there, right? It will occupy the body centered lattice point. Okay, suppose if you place the Cs plus at the body centered, how many atoms will be there in the surroundings? 4 atoms at the corner, above corner, and 4 atoms below corner, right? So total 8 atoms will have the direct contact with the Cs plus ion. So coordination number of Cs plus is 8. At the same time, if the atom at the corner is there, now it is shared with 8 other atoms, right? So Cl minus ions also will have the coordination number 8. Understanding? Is it clear? If you take the CaCl structure, Cl minus ions will occupy all the corners of the body centered cube, and the Cs plus ion will occupy the body centered lattice point. So complete it will form the BCC type of crystal lattice, and coordination number for both Cs plus and the Cl minus will be 8. Cs plus 8 because if you place any atom at the center of the body, there will be 4 atoms at the above 4 corners and the below 4 corners. So coordination number will be 8. At the same time, if you place the atom at the corner also, it is shared among the 8 members. So number of unit cells is how many? 1. Cesium chloride number of unit cells is 1. So it is a CSCl, CSBr, CSI, CSCN, and the CAS. These are the common examples for the cesium chloride type of structure. The next one is a fluoride, CaF2. So if you take the fluorides, cations will occupy the CCP type of lattice and anions will occupy the tetrahedral voids, because calcium is a bigger in size than the fluorine, right? So calcium will form the main type of lattice, CCP lattice, and the fluorine is the smallest size. As we go left to right in the periodic table, atomic size will decrease. So fluorine is the smallest size in that left to right in that period. So it will occupy the
tetrahedral site. But in this case, the coordination number will be different for both calcium and the fluorine. For the calcium, they have the coordination number 8, and for the fluorine, they have the coordination number 4. But total number of atoms per unit cell will be the 4. Effective number of atoms per unit cell will be the 4. So which is mostly common in the case of CaF2, SRF2, BaF2, BaCl2, SrCl2, CdF2, and HgF2. So these are the compounds which will show the fluoride type of structure. Okay, next one is the antifluorite. The difference between the fluorite and antifluorite is what? In the case of fluorite, cations will occupy the CCP lattice and anion will occupy the tetrahedral voids. And cation will have the coordination number 8 and anion will have the coordination number 4. But in the case of antifluorite structure, it is reverse. Anions will occupy the CCP lattice and the cations will occupy the tetrahedral voids. And the coordination number also will be different. Lithium plus will have the coordination number 4 and the oxygen minus will have the coordination number 8. So number of atoms per unit cell will be 4 in the case of antifluoride structure also, and which is mostly common in the case of K2O, Na2O, K2S, Na2S. Because what is the main reason? If you take the like K, Na, potassium, sodium and all belongs to first group, right? In the periodic table. So which is mostly common shown in the case of first group elements. Antifluoride structure, lithium, potassium, sodium. So lithium oxide, potassium oxide, sodium oxide, potassium sulfate, sodium sulfate, all will show antifluoride structure. Antifluoride means what? Anions will occupy the CCP lattice and the cations will occupy the tetrahedral voids. So lithium will have the coordination number 4 and oxygen will have the coordination number 8. So this is and all you have to remember compulsory as a tabular column with examples. Is it clear? Any doubts in this?
No, sir.
So there is no other go, you have to remember compulsory, because there will be some questions in the previous year questions also on this topic. Hmm? So next you are going to revise the complete formulas and all what are the important things are there, okay? Just wait a minute. Suppose if you take the contribution part, so first we'll start from there itself. So contribution of each atom from the corner, how much? Contribution of each atom from the corner, how much? What is the contribution fraction? Hmm? There is some network issue is there. But what is the contribution of each atom from the corners and all? You remembered or not? So just we'll revise quickly what we have done in this chapter completely. First, the contributions of atom to unit cell. So from the corners, what is the contribution part? What is the contribution part from the corners? One by eighth, right? From the corners, the contribution part will be 1 by 8. From the face, what is the contribution part? It is half. Okay. Okay, from the edge center, what is the contribution part? 1/4. Okay. Next, if the atom is at the body centered now, the contribution will be completely 1 atom belongs to complete cell. This is the contribution parts, which is very important. Okay, clear or any doubts? Next one, this is the starting numerical part is studied in the thing. And the next one is the important thing is, what is the radius ratio? What is the radius ratio to the radius of the sphere in the case of tetrahedral void? R is the radius of void and capital is the radius of sphere. Then what is the R radius ratio in the case of tetrahedral? R equal to 0.225 capital R. What about the octahedral? What is the radius ratio formula in the case of octahedral? Octahedral radius ratio is R equal to 0.414 capital R. Okay, 0.414 capital R, that is the octahedral void radius ratio. Okay, next one, based upon this radius ratio only we have the different rules, right? So if you have the radius ratio like R plus to the R minus in between 0.155 to 0.225, then what is the type of, what is the coordination number? What is the coordination number? Coordination number will be 3 and the structure will be, what is the structure? Planar triangular. Okay, if it's 0.2252 to 0.414, what is the coordination number? First unmute yourself and you can answer the questions. Shruti, what is the coordination number? Neha, Jafar, Ramcharan, Vishwanath. What is the coordination number? It will be 4 and the shape is tetrahedral. Next 0.414 to 0.732, the coordination number will be 6 and the shape is octahedral. And 0.732, when the coordination number will be 8 and the shape is body centered. Okay, these are the coordination numbers. So corner we have the coordination number 1/8, face we have the 1/2, contribution part, edge center we have the 1/4, and body center we have the contribution part 1. So these are the two important radius ratios. Tetrahedral void radius ratio is small r equal to 0.225 capital R. And the octahedral void radius ratio is r equal to 0.414 capital R. And trigonal void, there is one more void will come. Trigonal void, it has a radius ratio of 0.155 capital R. Okay. So after this, we studied about the number of voids and spheres in the pattern. Suppose if the spheres has an sphere number is n, then total number of tetrahedral voids how many? What is the total number of tetrahedral voids and octahedral voids? If the spheres are n number is there, then what is the total number of tetrahedral voids and octahedral voids? What is the answer? Hmm? Octahedral voids will be n, tetrahedral voids will be 2n. And this is the important formula. Next one. No, I didn't say what is the distance, okay? Relation between nearest to neighbor of atoms. Nearest neighbor distance. That is the D. And edge length A of cubic unit cell. Okay. Suppose if you had taken this simple cube like this. In the case of simple cube, atoms will be there only at the corners, right? So this is one corner, this is another corner. So atoms are there only at the corners. So this is one atom, this is another atom. So they're asking the relationship between the nearest to neighbor distance. They're asking the distance D. So nearest to neighbor distance is nothing but the D value, the distance between the two center of the atoms. So from here to here. So in the case of simple cube, these are the two atoms and these are the two nucleus also of the atom. So D is nothing but the A value only, right? That is the edge length only, right? In the case of simple cube, yes or no? So in the case of simple cube, the nearest distance between the two atoms is equal to the edge length. So simple cube A equal to D, where D is the nearest distance. Next, body centered. So what is the body centered? What is the condition for body centered actually? Root 3 equal to 4r, right? So if you take the nearest distance now, that is B equal to A by root 3. That is the relationship. In the case of face centered, it is D equal to A by root 2. That is approximately equal to 0.866A. This is approximately equal to 0.707A. Okay, these are the relationship between the nearest distance atoms and the edge length. Next one, relation between the A and R. In the case of simple cube, what is the relation? A is equal to 2R, right? Okay. in the case of simple cube, the relation between the A and R is equal to A equal to 2R. What about in the case of FCC? What about in the case of FCC? Root 2A equal to 4R. Okay. In the case of BCC, what is the condition? Root 3A equal to 4R. Okay. So these are the conditions in the case of simple cube A equal to 2R, FCC root 2A equal to 4R, BCC root 3A equal to 4R. Fine. Any doubts in this? Just I'm writing all the whatever the topics or formats are discussed in previous complete chapter. Only this is the new topic, D and A distances. Next, new density formula again. Density is equal to Z into M by A cube into NA. That is the density formula. Where Z is the effective number of atoms. M is the molar mass. A is the edge length. And Na is the Avogadro constant, that is the 6.023 into 10^23. Okay. So next, whenever there is a radius of cation and radius of anion is given, okay, they will give the radius of cation and radius of anions, and along with the edge length. How you will find that one? So in the case of FCC, what is the condition? Root 2A equal to 4R, right? That means root 2A equal to 2 times of R plus plus R minus. If you solve this one now, what you will get? A is equal to root 2 R plus plus R minus. We'll use this formula. Okay. But for NaCl structure, we'll use R plus plus R minus equal to A by 2. This is a formula we'll use for the NaCl structure whenever the radius of cation and the radius of anion is given along with the edge length. Suppose in the problem they will give edge length, they will give radius of cation. They will ask radius of the anion. Then you have to use this formula. Okay, in the case of BCC also same. Root 3A equal to 2 times of R plus plus R minus. In the case of simple, what is the formula? A equal to R plus plus R minus. Okay, simple they will not come mostly, but these two are the important formulas, BCC and the FCC. And the last one is a Bragg's equation. This is also important. Two d sine theta equal to n lambda, where d is the distance between the atomic planes, d is the distance between atomic planes. That means one row to the other row. What is the distance is there? That is a d. And lambda is the wavelength of the X-ray used. Okay. So again, the meeting is going to end here within less than 1 minute. So just you join once again. Okay. So meeting is going to end in less than 1 minute. You join it once again. So there's a Bragg equation 2d sin theta equal to n lambda.